remind you of the formula that we're using. And again, remember, this is just a fancy version of your slope formula. So we are just finding the slope of that secant line. It's just because it's not a line, we're not calling it a slope anymore. We're calling it an average rate of change. And because it's a function, we have it in function notation. But other than that, it really is just our slope formula. So I'm just generally going to kind of try to work a little bit, hopefully behind you guys, so you kind of check yourself as we go along. Now we could do this all here at the same time, or we could kind of go off and evaluate, f at 3 and f at -2 over here, and then bring them back, whichever way is more comfortable. I think I did it that way yesterday, but we could certainly just do it all at once. 3 times 3 squared minus 5. That's our f at 3 minus the quantity 3 times our -2 squared minus 5 all over our 3. It's going to become plus 2. Got some different suggestions. All right. I don't know what it is yet. I haven't finished. So 3 times 9 minus 5 minus 3 times positive 4, because we are squaring that whole negative, minus 5 over 5. What? 27 minus 5, so 22 minus 12 minus 5 is 7 over 5. So 15 over 5, and yeah, it's the 3 I've seen a fair amount of up there. Now we don't have any units for this function, so we don't know what our x's and y's are called. So really our average rate of change is just 3 here. Remember from yesterday, if we had units, we'd want to interpret that. So really this is 3 function values per x value, whatever they happen to be. Questions about any of that from yesterday? We will hopefully a quick review. How is everybody doing this morning, by the way? Everybody doing good? That's good. See, I did want to ask, I think, Crystal, you'll probably be good at it. Crystal, if you could keep an eye on the chats and see if there is a question that was asked there that I am not seeing or responding to kind of, wave me down or say something, or just
I'll do my best.
Thank you. I am finding that there's a lot to look at here, and I'm not used to it yet. Okay, so what I wanted to talk about today was a slightly modified version of this formula. That's going to be something for those of you going on to calculus that you'll use pretty much daily in calculus. That does work nice. And that's to take this average rate of change formula and modify it a little bit. Instead of looking at, instead of looking at 2 points x1 and x2 and looking at their function values, f of x1 and f of x2, we're going to change this a little bit to have only a single x value, and instead of the two x's, we're going to look at one of the x's and the difference between them, this length h, that distinction between those 2 points. So instead of x1 and x2, we'll just call this f at x. Just call that x. Erase all these while I'm at it. So we'll just call this x, and this will be x plus that h. So it's still our 2x values. Like if this was a 5 and a 12, then we'd have 5 and 5 plus 7, the difference between them. So this would still be f of x. This would just become f of x plus h. So it's the same pieces, just instead of dealing with the two x values, we're dealing with one x value and the amount of change. What that does to our formula up here, it does turn this f of x2 into f of x plus h minus this f of x1 is just our good old plain f of x. And one of the reasons we do this is this denominator here, this x2 minus x1, that difference is just this nice length h. So it does kind of simplify our denominator down to a single term as opposed to this multi-term denominators. In this form, we call this the difference quotient. Talked about this at the end yesterday. Difference quotient is just a quotient, a division of differences, and that's this quotient of those subtractions. Here, the difference between our inputs is just labeled as that h. But hopefully this does look like it is really just this formula in slightly different notation. So this is still just a version of slope, just one in a very particular notation. So if we want to apply the difference quotient to something, it is a method of finding slope, just like the average rate of change is, but it does have some advantages if we want to use it on something like an entire function kind of at the same time. I'll show you what I mean. If we have f of x equals, say, x squared plus 2x, and we want to apply the difference quotient to this function, we'll essentially be doing the same thing we did up here, just with our slightly different inputs. So the f of, what color here? The f of x plus h, this piece, we're going to evaluate this function at x plus h. So that x plus h is going to go in for those x's. So x plus h squared plus 2 times x plus h. So that's our, and I am going to put big parentheses around that, minus the function itself. So minus this function itself, minus, and we just have the function here, x squared plus 2x. And that's all still just going to be over that nice h. Now notice here we're not having to put in particular values. We're being able to do this, or we're able to do this kind of in abstract form all at once. And that's going to be one of the strengths of doing this tool this way. Now we do have to simplify this numerator. That can take a little bit of work. I'm going to give you an example to play with in a bit, but I want to walk through this one. So this x plus h quantity squared, we did that a fair amount of that yesterday, so that's just square the first, twice the product, square the last, or you can formally FOIL that out if it helps. Plus, going to distribute that to 2x plus 2h minus. Okay, we've got to subtract this, make sure this negative distributes. So x squared minus 2x after the distribution, all over h. So there's a fair amount of little, fiddly bits in your algebra you got to be careful with here. And that's actually one of the reasons we're playing with this tool, is it's a nice tool for practicing those little manipulations, nice tool for practicing, evaluating functions with expressions in other formula, all tools that we're going to need, as well as this preparing us for using this tool for those of you who are going into calculus. So we want to simplify this as much as possible. Notice this x squared and this x squared will cancel. This 2x and that 2x will cancel, they subtract off, and we are just left with our 2hx plus h squared plus 2h, these three terms, all over h. So one of the reasons that having this single term h down here is handy is because one of our big goals in using this tool is to try to get this factor of h to go away, get this factor of h to be out of our formula, because we kind of would love this h to become a 0, and we'll talk about why in a minute. But having this h down here evaluated at 0 would make us divide by 0, and we can't do that. So we'd like to get this h to go away. But notice with the canceling up here, there's a factor of h in each of these terms. So we can take this h and divide it into each of those terms, and it's going to cancel there. One of them is going to cancel here, it's going to cancel there, and we're going to be left with 2x plus h plus 2. So that's what we get when we evaluate this difference quotient. We have a fair amount of work going on here, but it does simplify down to this fairly straightforward 2x plus h plus 2. Questions about any of those mechanics before we talk about what this means or how we can use it? Again, I'll give you guys a chance to practice that in a bit, but you guys good so far? Good, good, good. Okay. So if we look at a quick graph of what this function looks like, it's got an intercept at -2 and an intercept at 0. That's a parabola. It's okay if you can't look at it and see that graph. We'll teach you how to do that in some of the upcoming chapters. But so that's our graph. That's -2. So if we wanted to take this difference quotient this 2x plus h plus 2, if we wanted to find an average rate of change between any particular locations here, say we wanted to find the average rate of change between, let's just say 0 and 2, go from 0 to 2, we could use this difference quotient to find it without having to do all of the mechanics for our average rate of change over and over again. So if we wanted to, that x would be our 0, the h would be a 2. So plug that 0 in. 2 times 0 is 0. Plus an h of 2 is 2. So I'm just going to plug those in. 2 times 0 plus our h. Again, remember the h is the difference between them. 2 plus 2 is 4. So the slope of the secant line between 0 and 2 has a slope of 4. And it will allow us to compute that for any starting value x and any amount of change h. We could calculate that rate of change quickly in a much simpler form than having to go through this average rate of change formula over and over and over and over again. So it's a little bit more work on the front end to get this nice simplified result. But if we want a lot of those average rates of change, we now have a very, very nice tool to do them quickly. But more importantly than that, what this is going to allow us to do is if we want to not find the average rate of change between 2 points, if we wanted to say find the exact rate of change at a single location, say tangent to that curve right there, say that's what, negative 1, 2, 3 at negative 3. So say we wanted to find the slope of this tangent line at that curve, at that point, or the instantaneous rate of change at x equals negative 3. If we tried to use this, finding the slope at a single point, as opposed to between 2 points, finding the slope at a single point is supposed to be impossible, because we'd have to take the 2x values. Let's actually find what this point is. Its x value is negative 3, and its y value would be negative 3 squared plus 2 times negative 3. So that would be, what, 9 minus 6. So its x value would be 3. That's cute. So 3. So if we tried to use this point for both our x1 and x2, okay, we'd have 3 minus 3 on top, so the top would be 0, but we'd also have an x2 minus x1. We'd have negative 3 minus negative 3 on the bottom, so this would both be 0. And 0 divided by 0 would be undefined. We wouldn't be able to find a slope with one single point, because we'd have to divide by 0 to do it. But notice in this difference quotient, we kind of got rid of that h in the denominator. So if we wanted to find the slope of this line tangent to the curve with the single point, well, let our x value be negative 3. If we only have one point, what's this h value?
Zero.
Yeah, it would be 0 plus 2. So negative 6 plus 2 is negative 4. The slope of this line tangent to that curve is negative 4. So we can find the slope of that tangent line from a single point using this tool. And in some ways here, we have cheated around the fact that we'd be dividing by 0 here, by kind of algebraically getting that 0 out of the way. Now, there are some problems with that, theoretically, that we'd have to solve, and that's essentially what calculus is about. Calculus is about figuring out how to justify some of the steps here to make sure that that dividing by 0 error doesn't cause a problem. But the reason that this difference quotient is kind of an important tool, an important key as mathematics goes along, is because it really does form the basis for differential calculus. because it's able to do something that algebra can't do, and that's this divide by zero finding points here. Now, we're not going to go quite this far with it. We are essentially using it to get us kind of used to the idea a bit, but mostly we're using it to practice this algebra, to practice those manipulation tools in such a way that when you guys get to calculus, you'll have, you'll recognize this tool and you'll go, oh, I can do that, okay. So you can focus on the calculus that you're learning. But we do want to take some time and practice these tools. So let's say we have a function, g of x. I don't want to be anything too horrible here. How about, oops, I don't know why I put that there. So let's take 3 times x squared, say minus 5. And I want to take that g of x and just going to say evaluate the difference quotient, which essentially means evaluate this, and your result should look something like that. So it should be a little function when you're done. So I'm going to give you a couple of minutes to do that. If you get stuck along the way, let me know. I'm going to write down what that difference quotient is just to remind us. So take a moment and try to do this evaluation of the difference quotient on the g of x, 3x squared minus 5. I'll give you a minute to do that. People often have trouble in this step where they're trying to evaluate at that x plus h. This x plus h can end up in kind of strange places, so do be careful with that. We are putting that x plus h into the function, into g, getting that 3 times x plus h squared minus 5, kind of like we did yesterday, and then that is coming back and replacing that, what's in those pink brackets. There's no significance to the brackets as opposed to parentheses, by the way. I'm just using them to look distinct to try to help us see things. As we do these again, I will kind of try to work behind you guys here so you can check yourself as you go along. Please don't be waiting for me. Please do jump in and try these. I often say the worst thing that can happen to you is you can get it right. Because at this stage, you don't learn anything when you get these things right. You want to get them wrong so you can learn from it and grow stronger. So you never worry about throwing yourself in and trying some of these things. Do be careful about this distribution of that negative. That's one of the places that a lot of people will go off the rails a tad, that negative has to distribute. That's why I like those nice brackets there. They help us stay straight. It might almost seem, I don't know, either magical or rigged or something, that everything without an H is going to cancel out here. This really does always happen when we're dealing with a polynomial. Whenever this g of x is a polynomial, these terms that have no h in them will always cancel out if we've multiplied everything out properly. So if you're ever doing this and these things aren't canceling and you're getting terms without h's in here, go up and look at all your distributions and your negative signs. Make sure you've found all your pieces, because they should all leaving you with just a nice factor of h on top here. Some people even, frankly, like to take the step of factoring out that h. So they can do this canceling all at once. If you like doing it that way, it's a perfectly fine way to do it. If you like what I did before, that idea of dividing the h into both terms, either way, we should end up with the nice 6x plus 3h. And that's our evaluated difference quotient. Now, it's not quite as nice as this. I mean, again, it was nice that all of these things cancel out, and that does happen every time it's a polynomial. But if it's not a polynomial, if it's a rational function or a radical function or something else, it can be quite a bit more difficult to make this h cancel. It can be quite a bit more difficult to simplify these. You'll get a little bit of a chance to practice that here, but mostly you'll learn a lot about how to do that and really practice doing a lot of that in calculus, where it becomes super important. Again, for us here, we're mostly using this as a way to practice these mechanics, get used to doing these kind of within function evaluations, and just kind of knocking off some of the rust about all this manipulation. Andrew, that worked out good? Anybody have any questions about those? Anybody questions or comments or thoughts? I do encourage you guys to practice those. They do make good questions for homework, quizzes, and tests and so forth. Again, mostly because under the kind of idea that this is a pre-calculus course, getting you guys some experience with these for when you hit calculus is kind of a priority. So making sure you get some of that practice. And again, it's not an uncommon thing to come up on things like tests and quizzes, as well as the homework. Speaking of homework, I did go check out how the homeworks are coming along. It looks like about half of you have gotten the, I forgot what it's called, that first homework assignment where you're just kind of playing with some of the old skills. About half of you guys have that done, but only about 2 people have started the 1.3 homework. So do make sure you're getting into those and starting to play with those. You'll want to kind of stay ahead as much as possible so you guys can come in and ask good questions and have time to play with those. So be careful about putting those off. That can become a very dangerous habit as we go along. So let me know in the chat whether you'd like to see another one of these at a larger scale. We can do one of these with, say, a rational or a radical function. So if you'd like to see that, let me know. Or if you guys are happy with this difference quotient idea and want to move on, then let me know that. So take a moment to express that preference, and we'll do one or the other. Justin, you wouldn't mind doing another? Anybody else? Crystal, like one more? All right, let's look at one that's not a polynomial, one that's got a little bit more going on. But I don't want it to be anything like terrifying. There are some that get just be nasty. And we generally keep them at a fairly reasonable scale here, but probably one of the more ugly ones that would be fairly legitimate to have down here would be something like, say f of x equals 3 over x plus 1. I mean, that might not seem like too terrible of a function. It's not. It's a fairly straightforward function. But the division in it is gonna cause some trouble. So given that function, take a moment, try to see what you would do to evaluate our difference quotient. There are some fun tools we'll have to bring to that. And while you guys work on that, I'm going to grab something to drink. These parentheses here aren't really doing anything, but visually they might be helpful. So anybody have any questions about that as the first step? Again, that process of putting this plus h in here, making sure that that x is becoming our x plus h, that step sometimes becomes the troublesome step for a lot of folks. But if you kind of keep in mind, if we were trying to evaluate this, say if we had x at 5, you'd put a 5 in for that x. If it was f at -4, you'd put a -4 in for that x. If it was f at star, you'd put a star in for that x. We've got f of x plus h, so that x plus h replaces this x. But of course, the question is what to do now. There are actually a fair number of good options, but I like to kind of go fairly fundamental with things here. So we do have two fractions that we're trying to subtract. So if you have two fractions that you want to subtract, common denominators allow you to subtract fractions. So we could find common denominators here and progress from there. But also we're looking at what's called a complex fraction. We've got fractions inside a big fraction. And anytime you've got fractions inside fractions, it's going to cause trouble. So my tendency would be to try to clear the fractions out of that numerator. And this is kind of a big version of this tool, but it is a tool that we're going to be using a fair amount. So this numerator has in it two denominators, and I'd really like it to not have any denominators. So if I want this x plus 1 to go away, I'm going to need to multiply this thing by x plus 1. Then that x plus 1 and that x plus 1 will cancel. If I want this x plus h plus 1 to go away, I need to multiply this whole thing by x plus h plus 1. That's going to make, excuse me, that's going to make this x plus 1 cancel with this x plus 1. That's going to make this x plus h plus 1 cancel with that h, or x plus h plus 1 when we do the distributions. Now, we're going to have to distribute this whole thing to both terms. So it's not going to be quite as easy as just those things cancel away, but it is going to get those denominators to go away. Now, of course, we can't just multiply the top of the fraction by anything we want. We have to also multiply our denominator by that same thing. So we're going to multiply that denominator by x plus 1 times x plus h plus 1. That way we're multiplying the same thing on top and bottom, and we preserve the balance of our fraction. So when this term distributes, when it gets to this first term, again, the x plus h plus 1s cancel. We're just left with the 3 times x plus 1 minus. Over here, The x plus 1's cancel, so we're just left with 3 times this x plus h plus 1. So 3 times x plus h plus 1. So that's our new numerator. And our denominator, we could multiply all this together, but frankly, I don't want to at this point. And it's a little bit disadvantageous to do it, actually. Leave this denominator all written out for right now. X plus h plus 1. So that step gets rid of the complex fractions, gets rid of the fractions within our fractions. And frankly, anytime we have fractions within our fractions, it makes our lives more complicated. So getting rid of them is almost always a benefit. I'm going to let you look at that step for a minute and try to decide what you might do next. While you look at that, if you have any questions about that step, I know there's a lot going on in that step. If you have any questions about that step, let me know. There's a lot going on in that step, so I'm a little nervous that nobody has a, hey, what the heck happened? You guys aren't just being shy, are you? Like us? No. Well, just to make a quick comment about that step, you've probably done things like it with, simpler scenarios. If we had, say, 3/5 plus 2/7 over, oh, I don't know, how about one? How about just 5? Nah, I don't want 5. I want 4. So if we wanted to simplify this complex fraction, we could certainly add these two together by making a common denominator of 35 here. But in practice, it's actually easier to, instead of using that 35 to construct common denominators to build it up, it's actually easier to use that 35 as a destructive tool to destroy those denominators. We have to multiply the bottom and the top by the same thing, of course. So we got to multiply by 35 over 35. But then when that 35 distributes, we get 3/5 times 35 plus 2/7 times 35. That's a 7. All over still whatever the 4 times 35 is. And the point of that 35 is it has both 7 and 5 as multiples in it. So that 5 is going to cancel, and that 7 is going to cancel. And we would get 3 times 7 plus 2 times 5 all over 4 times 35. And this is a much easier scenario to handle. We've got, what, 21 plus 10 over 140. So this is really exactly the same mechanic as this clearing fractions up here. It just looks a tremendous amount worse because of all the size of those expressions. And that's one of the reasons I want to make sure I'm pointing that out, is that one of the goals that we have in here in Math 111 is to take some of these tools that you have in your background that you maybe haven't used a lot, or think of as a very specific tool, and generalize them, make them a tool that you're using in a much more expanded way to do more powerful manipulations. So this kind of, expansion of, or more flexible use of a specific tool in your background, that's kind of one of the goals we have in here with a lot of your mathematics, to make them more flexible, make them broader tools. But we certainly have more to do down here, more to simplify. That's going to turn into a nice 3x plus 3. And we do have to distribute this negative 3. So we get negative 3x minus 3h minus 3 all over. Still going to leave this alone. X plus 1 times x plus h plus 1. But notice, just like it was doing before over here with our polynomials, this 3x and that 3x now, or negative 3x, now cancel. This 3 and that negative 3 now cancel. So that numerator has turned into a negative 3h over h times x plus 1, x plus h plus 1. So doing this manipulation kind of revealed those subtractions, revealed those cancelings that were much more apparent over here. Now this h will nicely cancel with that h. Remember, our goal was to get rid of this factor of h down here. We did bring an h in here, but it's no longer a factor, so it's not a problem. And we end up with a nice negative 3 over x plus 1 times x plus h plus 1. And you could multiply that together if you wanted to. Probably be nice to, but not worried about that today. So that was probably a more, I don't know, more dramatic evaluation of a difference quotient. And again, that's part of the reason why we're practicing with this tool, is because it gives us a chance to practice some of these little tools and these little mechanics that, they're not so little. They're fairly substantial uses of our tools, but they're uses of our tools ideally in ways that will make sense as we play with them and as we work with them. Was this example helpful or just terrifying? Helpful and terrifying? Both? Both is good. A little bit of terror is good. So do play with those homeworks for 1.3 and 1.4. I do want to start the section on lines, chapter 2, tomorrow. So make sure you start looking that over. A lot of the stuff on lines should be review, but depending on your background, that review might be a long time ago. So make sure you look that over. I do want to go through the lines section fairly quickly so we can get on to quadratics. We'll do a lot more interesting things in quadratics. So be playing with that 1.3, 1.4 homework, start reading your chapter 2, and have a wonderful day.
Thank you.
You are very welcome. Just